Okay, so what we're doing today is we are doing volume, but it always has a particular cross section. So every single one of these examples that we're going to do today is going to have a cross section that is a disc. That's the best I can draw a three-dimensional disc. That's the best I can do. I guess it probably maybe looks a little more like this. So it looks like a quarter on its side. It's round and it has a little bit of width to it.
Do you want us to draw that? Or?
It's up to you. I don't care. So every single cross section we're going to have today is going to be this circle. Why is that helpful for us?
Because you just do the circle.
We just do the area of a circle and then integrate it. So every single one of these is going to be pi r squared, just integrated with a different radius each time because the radius will depend on the function.
Wait, it's that easy?
Well, it's not that easy. Well, yeah, it's not easy.
It sounds that easy.
Okay.
Oh, this sounds too easy. Like your mind.
Is this a example or what's right?
Well, we're going to write something first and then do an example.
Are the notes going to take the full class?
I'm hoping not.
Like, are we going to have time for homework?
I hope so. I hope so. Your homework is just one question,
How many parts?
about the same as it'll take one of these examples.
But our homework's one question.
Yep.
It does make sense. There's not two of them. Like you literally can't make it less than one question. and still
That's
have
true.
the same. That is quite literally the least she could have given us.
Although we are looking at the same cross section each time, it could be a different axis of revolution. So we could be rotating around the y-axis or a line that runs parallel to the y-axis, or we could be rotating around the x-axis or a line that runs parallel to the x-axis. So a horizontal axis of revolution.
What about like the z-axis?
No, we're not doing that. A horizontal axis of revolution would be in terms of x. Okay, so horizontal is in terms of x, vertical will be in terms of y. So for a horizontal axis of revolution, we would do the integral from a to b of pi r squared dx, because our radius will be something in terms of x. If we were looking at the x and the y axis, our general shape would look like this with our cross section coming out perpendicular to the x axis.
What is going on? What?
As we're looking at the x and the y axis, this is approximately what our base would look like, or what it would look like before it was rotated, which means our cross section is coming out perpendicular to the x axis, which is why it's an x variable volume.
Yeah.
It's rough. Like the pictures are rough.
So
All you have to understand is that horizontal is perpendicular to the x-axis, so it's in terms of x.
is that like a quarter of a circle? There?
Yeah, kind of.
But you
It's
were
just one
saying
little section between x and y.
That's rough.
That is rough. It looks worse than it is.
Are you going to give us an example for this?
We are going to after this, we're going to do vertical, then we'll do examples of both.
Okay.
So then we can also have a vertical axis of revolution, which, what do you think that's in terms of? Y. Which means that our volume integration would go from c to d, which are the parameters it would give me, of pi r squared dy, where our radius would be in terms of y instead of x. And our cross section would be perpendicular to the y-axis. Yeah, they're not the prettiest, but
So we don't have to draw them.
as long as you know where the cross sections come out of, I'm okay.
So So it's opposite what you think.
Yeah, pretty much. Well, not really, I guess.
Perpendicular.
Right, so vertical is perpendicular to the y, horizontal is perpendicular to the x.
I'm very tippy.
So we are going to do an example. We actually have 4 examples.
Let's do 3.
Sorry, 5 examples, just kidding. We might not have to do them all. So we're gonna start with this example, which asks us to find the volume of the solid formed by revolving the region bounded by the function sine of x and the x-axis from 0 to pi.
This is where it gets hard.
And this will be an x-axis rotation, which means it'll be a horizontal.
Is that 0 to 1?
That is 0 to pi, yes. Again, I personally think it looks worse than it actually is, but I'm a little biased.
Wait, so never mind.
The first thing I do always is draw a picture. So from 0 to pi, I just go ahead and graph my function sine of x, which looks like that. That's what it looks like from 0 to pi. I know since this is a cross section, or since it's being revolved horizontally, my cross section is going to be vertical. So my cross section would be any vertical slice that I can take out of this shape.
So is the top line of that rectangle like perfectly
It's so
horizontal?
small that it pretty much comes out perfect with the graph.
But is it supposed to be on the curve?
Yes, it should go directly up to the curve and that's it.
Like, is it like, or is it like,
It's so small that it appears flat on top.
huh?
When we draw it, we can't draw something that small. So it looks like it doesn't fit when in actuality, if we actually took a slice, it would be so small that it would fit.
I don't like that at all.
I know.
Drawing it like it's a curve.
I know. That's fine. If that's how you draw it, that's okay. It doesn't change anything if you draw it like it's slightly curved on top. It also sometimes helps for me if I know what my revolved solid looks like. So if we were revolving this horizontally like it says we are, I'm gonna do this the best I possibly can. It would create like a football shape.
What the?
We're not
Because-
even doing a disc though.
It is being, yes, this is a disc.
Well, that's not what we're finding.
Yeah, we are. We're integrating the area of each disc within this football. That's what volume is. So basically what I did is I took this shape and I just rotated it around my x-axis,
So we're kind of like doing a Riemann's own volume.
pretty much, which is just integration because we have an infinite number of rectangles.
That's
So you really don't have to know what the three-dimensional shape looks like. It's not really that helpful because it doesn't change anything, but I like to draw it anyway. She's ugly, but we can kind of tell what she looks like. The important part is that our cross-section is a disc. And I know the area of a disc is what? Pi r squared. So in order to integrate this, I just have to figure out what my r is in terms of x. My radius for this football shape is the distance from my x-axis to the outside of my graph, right? Because that's a halfway distance around this whole thing. Which means on my two-dimensional, my radius is this, and it changes for each x value that I have. So how do I find that blue radius length right here? It might be 1 at a particular point.
It's
No, hold on, I heard it. It's just sine of x minus 0. Because it's the distance between my sine of x graph and the x-axis. So it's just going to be sine of x for that radius.
So we always have to minus 0?
No, but here it would be minus 0 because that's my lower bound for this.
Because that's where it starts.
Right, sometimes we might have another graph that we would subtract whatever g of x is, or whatever that lower graph is.
So like if it was from 1 to pi, then you would do sine minus 1.
Right, so no, if it started at 1 here, I
Yeah,
would do
that's what
sine minus 1, yes, yeah. Okay, so my radius is sine. Do we all see that? Do we see y? Because it is my function. That determines what my y values are at each of those x values from 0 to pi. So now all I have to do is take sine, put it in where r is, and then integrate on my bounds.
Whoa.
So it's going from pi or 0 to pi. Right?
It's going from 0 to pi, so those are my integration bounds. And then my area function is pi sine of x squared dx
Should it be decimal?
Yeah, it'll be a decimal. What? Yeah, you can do it. You also can do it. You can. It just, I prefer not to. Oh, on this computer. What do we get? 99348.
Yeah.
Okay.
4.935.
So that would be my volume. And if we had units, we would do the units.
So we're gonna be units on the homework.
So we're done.
That was it. That's it for that problem.
So what can you do to make this problem work?
Well, I could have a different function here and I could just be finding the distance between the two functions, but that just splits it. Like it really doesn't change anything.
Wouldn't you just do
Wait,
like
so what would you do?
minus the other?
You would just do one function minus the other one, which would make your radius a little more complicated, but really not really. The process is still the same. The hardest part is just knowing what your cross section is, but since all of these are the same, the process will be the same. So let's do another one. Ouch.
How is it a different step if we're doing that?
If we're going y-axis, yeah, we're gonna do one right now.
Alright.
Why?
So this one asks us to find the volume of the solid formed by revolving the region bounded by the graph of y equals x squared plus 1 and the y-axis between y values 1 and 5 about the y-axis, which means that it's going to be a vertical revolution. Just like before, I definitely want to draw this because that, I don't know, it always seems to help me. We're going to start by just drawing y equals x squared plus 1
Start drawing flip
on the
bounds.
bounds that it gives me. Goodness. So it told me I'm only looking between y equals 1 and y equals 5. So those are the only bounds I really care about there. And then it also tells me that I'm bounded by y equals x squared plus 1. So that's really the important part that we care about. And y equals x squared plus 1, bounded by the y-axis, is just a parabola, or part of a parabola that starts at 1. So that's what it looks like two-dimensionally.
Is it just going to 5? Or
Yeah, it's just going to 5. So if you want, I like to draw a dotted line showing any of my other bounds. And it tells me I'm bounded by this curve and the y-axis. So this is the region that's rotating, if that helps you as well.
So then, is it a half of a circle? Or is it still?
Technically, that's half of or a section of a parabola, not a circle.
So we don't have to do like.
No, because our cross-section is still going to be a circle. So my cross-section is still coming out of right here. But when I do the whole thing, it's going to be a cross-section that comes out of the whole thing, not just that little section.
So when we,
Yes.
would the solid of this look like an upside down hill?
It would. The solid of this would actually look like a bowl that's filled in. So it says I'm rotating around the y-axis, which means that it's going to look like this, just rotated around.
That's actually really.
Oh wait, I look again.
Yeah, so some of them are easier to visualize than other ones. I personally think anything that has a flat surface is easier to visualize a three-dimensional curve than something that's completely rounded like the previous problem. It doesn't change anything though. So it still means that my cross-section is the disk that is cut out perpendicular to the y-axis at an infinite number of places on this bowl. I'm gonna call it a bowl.
Will we need to know the shape?
You do not necessarily need to know the shape, you just need to know the shape of the cross-section. Although it is helpful to kind of see where it comes from.
So it's just like spinning around.
It's just spinning around, yep. So now what we're gonna do,
That's why it's a circle.
yes, that's why it's a circle, is we're going to set up our area. We're gonna find the radius, and then we're gonna integrate, and then we'll be done. So since my cross-section is a circle, my area is still pi r squared. That is not changed here. And I know that if my cross-section is a disk, the radius goes from the center out, right? That's what the radius on each of my cross-sections is gonna look like. It rotated around the y-axis, so I know that my radius is centered right here, although technically that doesn't really matter that much. So I need to calculate that radius. How do I find that radius?
I guess you can. We're done.
Wait, is it
Use
use
the
the
track.
y equals?
It uses this equation. Because this equation dictates every point here, and from here to here is the radius of each one of my disk-like sections.
D minus.
But this is a vertical rotation, which means I'm not using the equation in terms of x. I'm going to be using it in terms of y. So I need to change the equation that I've been given to actually find the radius that I'm talking about.
Wait. So to get the radius of y, you need to be x.
To get the radius of something rotated around the y, it has to be in terms of y. And right now it's in terms of x because x is on the inside. So I need to get y on the inside of that equation. So my radius is going to be equal to the y equals x squared plus 1 in terms of y. So what am I going to do to get the x by itself on this particular equation? No, I'm not going to delete it. What am I going to do?
One to the other side.
Subtract the 1 to the other side, then I have y minus 1 equals x squared. Then what? Square root the whole thing. Because then when I square root an x squared, it just becomes x. When I square root the y minus 1, do I want a negative number? Is my radius ever a negative length? No. So I only care about the positive of the square root of y minus 1. So that means this is the radius of each of my disks. Because because that tells me the x value of the outside of my disk from the center of the y-axis. So then I just put this in, so my volume goes from what to what? 1 to 5 of pi square root of y minus 1 squared dy. And you can put it into your calculator.
One to five.
1 to 5. What did we get? 8 pi, yes.
Oh,
Which is 25 point something rather.
Okay, can I put this?
If you have the decimal, that's fine. So 25.1327, right? Okay. Either one of those are acceptable.
There couldn't possibly be anything else to do. We should just stop here.
You don't want more examples? I would want more examples.
give us the harder ones.
You have 3 examples left. I mean,
Yeah, but I need to have the homework because I need.
okay, so how about we do 2 of them?
Okay, let's just do.
Let's just do one more. It's the hardest one.
2 examples. I think 2.
Okay, let's go. Let's just argue.
Okay, so this is the 3rd example.
Well, that's the first part of the question right there.
So this says to find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1.
Oh, I just
Told you
read
you
up how
wanted
we're
more
using
examples.
circles.
Yeah, because everything's a circle.
So this is gonna be a disk rather than a plate.
Still gonna
What?
Just
What we're doing.
It's only called a disc because it's moving.
No, it's a disc because it's round and flat.
But this one's gonna have a hole in it.
No, this one's not gonna have a hole in it. That would be a washer, which is what we're doing tomorrow.
I'm jumping off a bed.
Well,
Okay,
won't we just integrate 2 different things tomorrow? and interact with them?
yes, pretty much the same thing. Okay. So what we have here is different because we don't have a solid that goes down to any of our axes. So what it's gonna do is it's gonna basically look like it's hovering midair and then it's gonna rotate around a line that is not our axis. It doesn't change anything. So I'm still gonna graph it like normal. I know that I'm bounded by y equals 1, so I draw a dotted line at y equals 1, which just means that none of my initial graph can exist below that line because that's what I'm rotating around. And then the rest of it is bounded by 2 minus x squared. So I have to graph 2 minus x squared. I really should have gone.
I'm confused about the g of x equals 1.
What about it?
Why is it there?
Because that tells me that I'm not going below 1. G of x is the same as y.
Yeah, but isn't that the same thing as saying about line y equals 1?
Yes, but that is telling me that I'm bounded by y equals 1. This tells me I'm rotating around y equals 1. So what we're bounded by isn't always what we're rotating around.
So if you were bounded by that and rotating around y equals 0, you would have a washer.
We'd have a washer, yes. Yep. So bounds and where we're rotating around are not necessarily the same thing. So sometimes it'll look like something's repeated twice.
So like,
So, sorry, go ahead.
so like the last one, we were bounded by
The ground.
1 but rotating at 5.
bounded by 1 and 5, but we rotated this way, so it didn't matter. Tomorrow you'll see the difference between what we're doing today and what we're doing then. Okay, so what we have is we have an upside down parabola that goes through my graph or my y-axis at 2. So this is what it looks like bounded by my graph of y equals 2 minus x squared and g of x equals 1. So this is the section that is being rotated. Which direction is it being rotated? Is it being rotated horizontally like this or vertically like this? Horizontally, because it tells me it's being rotated around the line y equals 1, which happens to be this dotted line here. So it's going to look like a football, like the first example that we did. That doesn't change the fact that my cross section is still a disc. So it is still a circular cross section. It's just running perpendicular to that axis. Oh gosh, I can't draw 3-dimensional discs. I'm really sorry.
You do a really great 3-dimensional bowl. That was a good one.
Thanks, I tried. Okay, so far, what are any questions that we have?
Well, we're just one.
So far, we're not done. Like, are there any questions about how we drew it, how we knew what the bounds were, and how we knew the rotations?
So the only difference between this one and the other one was that the other one said bounded by the graph.
Right, bounded by an axis. This one's not bounded or rotated around an axis.
How do you get it to go to 2?
Well, I graphed it. So at 0, 2 minus 0 is 2. So that's how I knew. I just graphed the function. Yeah. Okay, so now what do I need to know in order to solve this problem?
The radius.
The radius. So on each of these discs, my radius goes from the center to the outside. Or essentially, it goes from here to here. Hold on, I heard it somewhere. What'd you say? Why did you know it was f of x minus g of x? Because we did that yesterday. So if I just did f of x, it would technically give me the height from that point on the graph down to the x-axis. But this told me that I was bounded by 1. So I just want to find the distance between 1 and the top of my graph f of x. 1 here happens to be g of x, so we just do f of x minus g of x for my radius. And then we simplify it out. So f of x here was 2 minus x squared minus g of x, which was 1, which gives me the radius 1 minus x squared. Are we all okay with that? And now all we have to do is plug it into our integral and then plug it into our calculator. So my volume would be the integral from what to what?
1 to something.
1
Or
to 2.
something to 1. Is it 6 to?
I haven't heard the answer yet.
It's not 1 to 2.
What is different here?
It's
Yeah.
We don't have our numbers, which means that we actually needed to find them.
so we have to say f. and g.
Oh, is it?
So we have to set f and g equal to each other to find these intersection points, which will give me my x bounds.
Why do you want x bounds?
Because I'm rotating horizontally, and it's all in terms of x, so my x has to be the bounds as well. So I take f of x and I set it equal to g of x, which means I have 2 minus x squared equals 1. And I just solve, so I'm going to subtract 2 across. I get negative x squared equals negative 1. Divide by negative 1. And I get x squared equals 1.
So x equals the square.
And what is the square root of 1, Deanna? And negative 1. So x equals positive and negative 1, which means that negative 1 and positive 1 are the bounds for my integral. So my integral goes from negative 1 to positive 1 of pi times my radius, 1 minus x squared, squared dx. So if we don't go down to the axis and it doesn't tell me between this value and this value, we need to find the intersection to figure out our bounds. And then you just plug this into your calculator.
What in the integral that was telling us that we're rotating through y equals 1?
It says about
Yeah, but
the line y equals 1.
what did that do to your integral?
It didn't do anything, it just told me the rotation. So that told me I wasn't going to the x-axis, but it didn't do anything to my integral. What did it to my integral was it didn't tell me between 0 and 5, or between, I don't know, x equals -3 and x equals 4. So the lack of that told me I had to set them equal and find the intersections. So if you look on the previous examples, I gave like a domain. This one I didn't give that. And the lack of that told me I had to use this. Had to use intersection. What did we get?
3.5510.
16 pi over 15.
I got 16 pi over 15, but that is equal to 3.3510. Again, if it gave us units, we would have to put units. Volume is units what?
Square.
Cubed. Area is units squared. You guys were so confident too.
It's just like
It was like
so
automatic. Yeah.
self-conscious, like unit squares.
Self-conscious.
Confidence?
No, it's just programmed into my brain that
Okay,
R squared
let's do one more and then I will turn you loose.
3D. You know what? They're just laughing at me. Anna's cackling.
Cackling.
She's squeezing that little thing.
Yeah, it's embarrassing.
It's embarrassing for you?
No, for me.
Leave him alone. He's living his best life.
Amanda does it pretty interesting. Yeah. You love it. It's just weird because I should watch it.
We should watch it.
I'll watch it. You
I did not watch it.
I don't think they asked Dylan on Snapchat.
Well, I had Dylan's phone
It's just
first, so
like I
he
know.
just like recommended me his app.
I don't remember one. He asked. Yeah, he asked for us.
He doesn't want me on Snap because he thinks I'm crazy.
I've talked for my story. I didn't.
Yeah, that way if you call off work and you're out, friends,
Cause I do that.
I never do.
I don't do that. I just don't want to. I don't want to.
I barely post to my story.
I barely post my things.
So this one asks us to find the volume of the solid formed by revolving the region bounded by y equals x squared, the x-axis, and x equals 2, about the line x equals 2.
Whoa, that's boring. Why do we have 3 things bounding it? That's
Because that is very important so we know which section of the graph we're actually rotating.
what is bounded lower than?
Okay, so this one is different. Let's go ahead and draw it and we can pick it apart from there. So when I draw this, it tells me that I'm bounded by the x-axis.
Okay, well, you're naturally bounded by the x-axis, so you have to tell us
You aren't necessarily always bounded by the x-axis.
in this.
In this one we are, but that tells me the section of the graph that I'm using.
Okay.
So I'm bounded by the x-axis and by x equals 2. Okay, that is very important here. I'm also bounded by the graph itself. So what I have to do is I actually have to graph the graph itself, right? So when I plug in 0, I get 0. When I plug in 1, I get 1. When I plug in 2, I get 4. So it's gonna be up here. So my graph looks like that. All I did was graph that section of the parabola.
Large problem.
It is. This will be vertical, so we will have to change it in terms of y. Good. But we're not there yet. Which section of the graph am I actually rotating? Am I rotating this part? Or am I rotating this part?
Oh, first.
First part or second part?
Wait, what?
Second part.
Second part. Because it is the section of the graph that is bound by the curve, the x-axis, and x equals 2. So this is the section that I'm actually rotating.
So it's like a weird shaped triangle.
So when I rotate it, it's going to look like this. Like a curvy cone, upside down.
Okay, so you drew a arc thing at the bottom there.
Yeah, because showing that it's rotating.
Yeah, it's okay, it's
it's
round.
making it
not
circular.
Actually arced at the bottom.
No, it's not actually arced at the bottom, but that it's round.
like
So it's
a-
rounded. But that's approximately what, like, it's poor drawing, but that's approximately what this is gonna look like when it's rotated.
How do you do it?
No.
Well, there's no good way to draw it.
Like an oval at the bottom, and then
I just, whatever works for you. Okay, so Erin already pointed out that this is a vertical rotation, which means each of my cross sections are taken perpendicular to the y-axis, which means I need to change my equation in terms of y. So I have y equals x squared is the equation I was originally using. How do I change that in terms of y?
Square root one.
Square root y. So I get x equals the square root of y. Do I use the positive and negative square root or just the positive? Just the positive because we can only have a positive length. So now here's the real question. If this is my cross section, actually it'd be like this. Because it continues on over here technically after the rotation.
Wait,
My radius is this section right here, right? For any given y value. How do I find that radius?
2 minus x.
2 minus the square root of y.
Well, 2 minus x.
Because
Wait, what, yeah, what is it?
we recognize that the square root of y gives me the length from the y-axis to the outside of my curve for any given x value. But I wasn't going from here to the curve, I was going from the curve to 2. So that means that this whole section is 2, which means when I subtract out the curve, whatever's left is my radius.
So it's just square root of y.
So radius is 2 minus the square root of y. And that came from my bound, x equals 2, and my graph, square root of y. So then we just go ahead and integrate.
wait, I was about to say,
So I have the integral of pi times 2 minus the square root of y all squared dy, right? What are my integral bounds?
0, 2, 0.
No, 0, we want.
Remember, we're in terms of y, so my integral bounds come from the y-axis.
0.
0 to 4, how'd you get that?
oh,
Looked at it.
I looked at it. So my graph started at 0, and my graph ended at 4, which is where it intersected x equals 2. So again, I could have just looked for the intersection. So it does go from 0 to 4 are as my bounds, and then I can just plug it into my calculator. Is this getting any easier?
I didn't understand that.
How did we get 4 again?
Because this graph intersected x equals 2 at 4.
Linda's thinking. Got the answer.
Yeah, it took my calc a little bit
To find out.
to process
Did you
that.
do your calculator, Linda?
Yeah, I was just about to ask.
I think I
Is that what you said?
What did we get as our answer?
8.7.
3775.
Okay, I apparently never finished on my notes, but that sounds right. 3775. Okay. And then it would be units cubed for volume. How do we feel about this?
Okay.
Yes,
Okay, so your homework is on Canvas. It is one question and it is due tomorrow.
Okay, wait, I'll just say it.
And then tomorrow we're doing washers, which is pretty